Welcome to The Explainer. Okay, today we are unpacking an absolute game changer from researchers at Stanford University and UC Berkeley. We're looking at a brand new framework that tackles one of the biggest bottlenecks in frontier AI right now. And our goal today is to understand exactly how we can stop AI judges from getting stuck in this frustrating loop of tied scores. It's going to be a good one. Here's the game plan for today. We'll start with Section 1, the AI judging problem. Then, 2, enter LLM as a verifier. 3, the 3 pillars of verification. 4, the round-robin tournament. And finally, 5, state-of-the-art results. Let's get right into it. Section 1, the AI judging problem.
So let me ask you a question. What happens when you evaluate two incredibly complex AI agents and they get the exact same score? Well, it's actually a huge headache. Right now, standard LLM judges use what we call coarse-grained discrete tokens. It's basically like asking an AI to grade a highly complex coding task by just picking a whole number between 1 and 8. It's incredibly blunt. It completely fails to capture the nuance between two multi-step agent trajectories that might be super close in quality but definitely aren't identical.
And the consequence of that blunt scoring? 27%. That is the tie rate on the challenging terminal bench evaluation benchmark when you use this standard discrete scoring. Just think about that. More than a quarter of the time, the judge just throws its hands up and says, they're both a 4. This creates a massive roadblock for us. If we literally can't measure which AI agent did a better job, how are we supposed to reliably build the best AI?
Section 2, enter LLM as a verifier. To fix this, there's a fundamental shift in philosophy here. Think about what a judge actually does. By definition, a judge forms an overall opinion and makes a broad decision. It's inherently subjective, kind of vibes-based, and, as we just saw, really coarse. But a verifier is totally different. It's designed to confirm absolute truth or correctness using incredibly detailed, granular evaluations. The researchers realized, hey, we need to stop asking AI to be this subjective judge and start engineering it to be a rigorous verifier.
Section 3. 3 pillars of verification. Okay, so how do the researchers actually build this general-purpose framework? They used 3 distinct scaling techniques. Number 1, scale, score, token granularity. Basically, instead of a scale of 1 to 8, what if we bumped that up from 1 to 20? Doing this drastically reduces quantization error, which lets us capture the underlying continuous rewards. Number 2, scale repeated verifications. A single check by an AI might be noisy, right? But an ensemble averages out those biases. And number 3, decompose evaluation criteria. Let's actually look a bit closer at that first pillar. The real magic here is how the math actually works under the hood. Instead of forcing the model to just pick one single clunky discrete score token, the verifier extracts what are called the top log probs. That's the top log probabilities from the scoring tokens, like score A and score B. By looking at the underlying mathematical probability the model assigns to each possible score, the framework calculates a highly precise, continuous reward. So instead of a rigid staircase of whole numbers, it maps this beautifully smooth curve of quality. Now, moving on to the third pillar, criteria decomposition. Instead of asking the AI to just take one giant holistic guess about whether a trajectory is good or bad, the verifier splits the whole evaluation into 3 simpler, complementary pieces, specifically specification, output, and errors. Let's break down exactly what those 3 slices mean. First up, specification. Did the trajectory actually satisfy all the specific task requirements, like specific file paths or naming conventions? Second, output. Does the format of the output perfectly match the expected result? And third, errors. Is the entire trajectory completely free of any failure signals or crash logs? By checking these 3 distinct factors individually, rather than just guessing all at once, the overall accuracy of the verification shoots way up. Section 4, the round-robin tournament. I absolutely love this analogy. Imagine trajectory A and trajectory B stepping into a ring together. Because we're now calculating these precise, continuous mathematical rewards using those log probabilities, we almost never have a true tie anymore. For every single possible pair of trajectories, the verifier just computes the reward for A, computes the reward for B, and compares them head-to-head. And here is the golden rule of the tournament, straight from the researchers. The trajectory with the higher reward receives a win, and the trajectory with the most wins is selected. It is so incredibly elegant. Because it's a round-robin tournament comparing high-precision continuous numbers across every single pair, it mathematically guarantees a decisive rank-ordered winner no matter how many candidates you have. Section 5, state-of-the-art results. Okay, let's talk data. When this was tested on the official Terminal Bench and SWE Bench leaderboards against frontier models like Claude Opus 4.6, GPT 5.4, and Gemini 3 Flash, the contrast in tie rates is just stark. Even if you give a standard judge 16 repeated verifications, which is a massive compute budget, by the way, it still struggles with a 5.4% tie rate. Give it just one verification, and it fails 26.5% of the time. But the verifier? 0%, flat, zero. Across all budgets, it entirely eliminates ties, every single time. But here's the thing, it's not just about breaking ties. It's about actually getting it right. Even at the maximum verification budget of k equals 16, the discrete judge tops out at 70.2% accuracy. The verifier, a commanding 77.4%. And even at k equals 1, just a single pass, the verifier hits nearly 75% accuracy while the judge sits at a pretty dismal 57%. So the verifier is maintaining this massive 7% lead in raw accuracy over the judge at all times.
So why does all this matter for you and the future of AI? Well, when researchers use this LLM as a verifier framework at test time to pick the best agent trajectory, the overall downstream success rate for the Forge Code agent jumped from an already impressive 81.8% to a new state-of-the-art 86.4% on Terminal Bench. This proves that having a better evaluation method directly translates to highly successful AI performance in the real world.
And honestly, the best part is how adaptable this is. LLM as a verifier is a true plug-and-play solution. It generalizes perfectly across entirely different agent harnesses. Beyond Forge Code, it boosted Terminus Cura to a 79.4% success rate, and Terminus 2 up to 71.2%. So this isn't just a one-trick pony. It is a fundamental upgrade to how we evaluate any AI agent. So what's next for this team from Stanford and Berkeley? Well, they're already looking at integrating this scalable verification framework directly into reinforcement learning training pipelines. They're also planning to extend broader support to process reward models, or PRMs, and outcome reward models. The general purpose framework they've built here is really just the foundation for entirely new paradigms of AI training.
Which leaves us with a fascinating thought to end on. With AI agents solving increasingly complex, long-horizon tasks every single day, how will we ensure we can perfectly verify the verifiers? It is an endless, fascinating loop of AI evaluation that will absolutely define the next decade of technology. Thank you so much for joining me for this explainer, and I hope it completely changes how you look at AI benchmarking.